So welcome, ladies and gentlemen, to this session on the route towards decarbonized transport. My name is Ingo Machenbach. I'm from Statkraft. I work in the hydrogen department, led by Björn Holsen, that you met earlier this morning. I also have worked previously in Statkraft with biofuels and in silver green fuel. And I'm delighted to chair this session. Cutting the emissions in the transport sector is of crucial importance, as most of you will know. If we don't do this, we will not reach the climate targets. So we have 3 research centers represented here today. All of these 3 centers were inaugurated in 2015. 2 of them are technology related, so which are biofuels, looking at biofuel production from resource via conversion and to a finished product. And then MoZEES, zero emission mobility, largely based on battery electric and hydrogen fueled. But then we also have NTRANS, an FME that doesn't only look at the technology changes that we need to do, but also looks at the societal changes that need to happen alongside with the implementation of new technology. Just a little practicality. It doesn't say so on the slide here. It says that we have it doesn't say here actually, but there was a break there before. I mean, what we're going to do is we're going to have 3 presentations here now. We're going to open up for a few questions after each of the presentations, and then we just carry into a panel debate that we'll rig here for you right after the last presentation. And I encourage you to ask questions to the speakers, and also later in the panel debate, challenge the panel participants with any questions that you so may have. So the first speaker is Kari Espegren from the Institute for Energy Technology, IFE, at Kjelle in Norway. Kari is a principal research scientist with more than 30 years of experience in energy systems modeling and also transition in the energy sector. And she will introduce the FME NTRANS for you.
Well, I'm not going to introduce the whole FME. I'm going to talk about what we have done within sort of the transition pathway study we have done. I'm research manager for the transition pathways in the FME NTRANS, and we have looked on the whole society, but now I will focus on the transition we can see in the transport sector for the future. So what do we do in this transition pathways studies? We look at how we can decarbonize, so this is low carbon transitions. And what we want to do is to understand both from the societal perspective and from the techno-economic perspective how we can work together and establish a bridge between the different disciplines of how to look into transition in general. So we study policy, we study social development, and we also use economic and energy systems model to analyze this. So what we have done so far in this research topic is to describe 4 different transition pathways to low carbon society, where we combine sort of the social science studies with the techno-economic and energy systems modeling. And I will show you what this can look like. So this is the 4 scenarios that we have been looking into, and where we look at sort of 2 different dimensions, where we have the socio-institutional dimensions, which say something about the actors and the society in general, how it can develop. We can sort of in the low bottom, the incremental innovation pathway, we have low social change or societal change. But in the social change pathway, we have a high social change, which means that we have do things differently. We can share. If you look at transport, we look at shared mobility, for instance, circular economy, while we in the incremental pathways do things more the way we actually do it today. And the second dimension is the technology dimension, where we have low or high technology change. So for the incremental pathway, will be more like business as usual. We use the technologies that we have today, step by step improve them, of course. So energy efficiency, electric cars, biofuels, for instance, are important technologies here. While in the technology change or technology substitution pathway, we can see that we work a lot with the research, technology development, and we use new technologies. Technology learning is higher so that it's cost effective to invest in hydrogen technologies, ammonia, CCS technology, and so on. And then we have the fourth scenario, the radical, which combines then high societal change with high technological change. So here we have also so both technologies, but also that the society are sort of more different. We travel less, we use sort of both person and freight and goods have lower travel distances, and this also decrease the energy demand in the radical transformation pathway. And we also in this societal change path, these two pathways with societal change, we have sort of more focus on local production of energy and also less export and import, at least in the radical scenario with the global markets. So then I would like to share with you some of the results from the analysis. And now I will focus on the results on transport. We have, of course, with this analysis, we could sort of look at power production, we could look on industrial sectors, on different topics, but now the focus is on transport. And here you can see the use of transport fuels in the 4 different scenarios with the incremental, societal change, technology, and radical transformation. And what is observed in all, and for all 4 scenarios, we have values for 2030, 2040, and 2050. So you can then see the development going from 2030 with rather a high share still of fossil fuels in the transport sector. All sectors are electrified in a high degree, but for the 2 scenarios with low technological change, the 2 at the bottom, we have a huge implementation of, or a high use of biofuels, and this is mainly imported biofuels, so it's much like we see today. But for the 2 scenarios with a high technology change, we see the introduction of both hydrogen and ammonia in the 2 scenarios towards 2050. And we also see that the energy demand, or the energy use is decreased, but that is not mainly due to the decrease in the demand for transport, even though it's lower in radical than in technical. But the lower demand is represented through the much higher efficiency of the electric drivetrain. So this result is a sort of the summary of the electricity use for the whole transport sector in the 4 scenarios in 2050. So what we can see, I'm not sure if it's easy to see, but the blue is light blue below the lowest one is energy use, electricity use for cars. So then we have for vans, we have electricity use in sea transport and also in air. And that's in all the 4 scenarios. But what we observe in the 2 scenarios with high technology change is that there will be huge amount of electricity going for hydrogen production. And this hydrogen is only the one, I've only included here the hydrogen that is actually used for transport in Norway. So in the technology change transition pathway, we see that almost half of the electricity going to the transport sector is for hydrogen production. And there are different segments of the transport that will be using hydrogen, but it's all sort of heavy. Yeah, it's road, it's maritime, and it's also some going for the aviation sector, but that is something that we can discuss later, whether that will happen or not. But there are a lot of uncertainties when we look into these studies of future development. There are uncertainties related to technology development, and we have to quantify sort of the stories of the transition pathways that are made together with the social scientists. And then there are a lot of uncertainties, and some of them can be sort of described as very important bottlenecks. It's related to the maturity of the technology option. It's related to how the new technology can be integrated in the system. It's about social and also political feasibility. So, and these sort of uncertainties we have addressed in the modeling work. And I will just show you two examples of how we can deal with that. One is related to the biofuel price, because when we can import a lot of biofuels, which we can do in the transition pathway with low technology change, well, we do so. We import a lot, and it's sort of an easy way of reaching our emission goals. So, but if we increase the import price of biofuels, what happens then? I will show the results later. And we all have done the same with sort of technology learning or with investment cost. If the investment cost is not falling or reduced as fast as we believe it will, what will then happen? So we have tested that with the technology costs for hydrogen technologies in the 2 scenarios with high technology change. So here you can see the impact of a higher price of the imported biofuels. So there are 2 sort of main takeaways. The first one is that the transport sector will use a lot more fossils, so because there are not that many options. And the second one is that also in these scenarios with low technology learning, we will have an introduction of hydrogen, because we need to achieve certain emission reduction levels, and then hydrogen become competitive when biofuel prices increases. And then the impact on technology learning for the hydrogen technologies. And here I've only included the 2 scenarios with a high use of hydrogen, the technology and the radical scenarios. And then we see we have sort of numbers for the REF with the high technology learning and the new analysis with the lower technology learning for 2030, 2040, and 2050. And what we can see for the 2 scenarios is that this reduces the use of hydrogen in both scenarios, and we also see a rather major decrease in the use of blue hydrogen in the technology scenarios. So what this tells us is that we need the technology learning to have these technologies, to have the higher implementation rate of these technologies. So I want sort of to end my speech with saying that it's possible to reach really high levels of decarbonization in the transport sector in Norway, but this needs a rather huge change, a high degree of change, both in technologies but also in society. There are a lot of uncertainties, especially related to maturity of technologies and related to acceptability in the society, and also the willingness of policymakers to have policies in place that really can help us with the transition, such as CO2 taxes or incentives that can reduce the cost of investing in new infrastructure. Yeah. So it's important that we address all these different bottlenecks in this transition so that we don't slow down the transition. And if you want to read more about this work we have done, here's a link to the latest report on this work. And thank you for your attention.
Yes, I think we have some time for questions. Are there any questions in the audience you want to address to Kari on the results from NTRANS? Don't be shy.
I can't see you because
Yes.
there's a very bad light.
Somebody with a microphone coming over to you just now. Just come stand. Stå her.
Ja, det er så vanskelig med lyset.
Sorry. My question was, what's the price of hydrogen inputted in the model to make it viable for future scenarios, considering also like the low round-trip efficiency compared to batteries? Thank you.
We don't sort of have an external price. The price of hydrogen is an endogenous, it's a calculation by the model. So we have the resources, we model sort of from, so hydrogen is produced either from natural gas, blue hydrogen with CCS then, or from renewable electricity. So we invest in all the different technologies to produce hydrogen, and then it's a result of this optimization. And it's not sort of one price, because for electricity, for instance, the electricity price is a very important input to the hydrogen production. And then the electricity price is fluctuating sort of every day, every hour. So I can't give you one price, but if you want to know more, but what we see here is that it's actually a chosen technology, so which means it's cost competitive when it appears in the modeling. Yeah.
There's another question over here.
Hi there. I'm curious if you have independence between ammonia and hydrogen, or do you have, that an increased hydrogen market would also stimulate an increased ammonia market?
Well, I'm not quite sure if I get your question, but I will try to answer if I understood it correctly. So we have different technologies that can use ammonia or liquefied or compressed hydrogen. So it's sort of, it's chosen by
So was it assumed to be just independent choices, depending on technology? There was no coupling between the two?
No, but it might be sort of cost effective to have a huger production of one than the other. So there are some interdependencies, but yeah.
We have time for one more question.
You mentioned about the biofuel, but the biofuel you mentioned that it's going to have to be imported.
No, it doesn't have to be imported. We also produce biogas and biofuel domestically. That can be used in 2 of the scenarios, and in 2 of them we can also import. But it's restricted, in 2 of the scenarios, and in 2 we can import as much as we want to, for a fixed price.
And that's what I was thinking, that the importation, then you're going to spend more kind of energy to be able to bring. Did you take into account that?
Well, we take into account the transport of energy, yes. But not outside. In this model, we don't take into account the transportation outside Norway.
Yeah.
No.
Okay, thank you.
Okay, thank you very much, Kari. One more round of applause. So the next speaker is representing the Center Bio for Fuels. Just for the sake of openness, I have been part of Bio for Fuels for many years myself. And we have here Judit Sandquist from SINTEF Energy. Judit is a research scientist at the Department of Energy at SINTEF. Judit has 20-something years experience with production, research and production of biofuels, and has also worked for more than 10 years with sustainable aviation fuel. Thank you.
Thank you very much, Ingo. So as Ingo said, I'm representing the Biofuel Research Center and Bio for Fuels, as the name saying. I've prepared the slides together with the center leader, Duncan Akbaruyat. Here you can see why do we need a research on transport. 1/3 of the Norwegian CO2 emissions are coming from the transportation. Half of it is coming from the road transport. On the right-hand side, you can see how it is been in the last from 1990. And you can see that the emissions from the road transport has been declining since 2015. This is because of the introduction of the biofuels as a blending mandate. This sector is electrified too, so you will have a much higher effect of electrification afterwards. But this decline is mostly because of the biofuels. And the Norwegian government has recognized the role of biofuels by setting an ambitious mandates more or less everywhere in all the transportation sectors. And they have even more ambitious targets for 2030. And these are quite high. So these are to be contribute to 40% of the emission reductions. So it is nice and well, and as you might guess, we are doing the easy way, we're importing everything. Is it good? We don't have production at scale in Norway. And why is it important to have that? We need to have a security of supply. We need to have workplaces, and then we need to have an increased control on the sustainability. The control on the sustainability has been debated lastly. So if you do it inside the country, you have much better control. So what we do in Bio for Fuels to accelerate the biomass and the biofuel production in Norway. We focus the technologies relevant for Norway. Norway doesn't have the feedstock that the biofuels are produced of today. We don't have advanced biofuel production almost anywhere in the world. It's very, very small. And when I say advanced biofuels, I'm referring to the European definition. The Norwegian is a different definition, so we do use advanced biofuels in Norway. But we have wastes and residues and byproducts from the forest industry, from the forestry, something from the agriculture, not much, and also wastes and residues from other type of industries. The conversion technologies are not commercial for these technologies. But we do have stakeholders in Norway that want to commercialize those technologies, want to bring them on market. So we are working together with them to accelerate their efforts. In addition, we are contributing to high-level scientific work in the different committees. And also we're focusing on bringing the knowledge to the public. So we have, for example, a webinar series. It's 1 hour webinars and giving you a knowledge on quite many different aspects of biomass, bioenergy, and biofuels. And I have some examples of the results we have in Biofuel Center. Here you can see the structure just really quickly. In the middle, we have the technical value chains. The technology research is going on there. We are working on the end use, the techno-economics, and also we dedicate a lot of research on the bioresource. The sustainability of the biofuels is very, very dependent on the resource you're using. So here in Norway, we have, for example, developed a tool that will help the local authorities and local forestry owners to decide on how they do the forest management. So here the tool will predict the local surface temperature, depending on what kind of forest management you're doing. Another example is the logistics. If you build a plant, it's very important that you source your biomass. There is a lot of failed efforts worldwide because they couldn't source their biomass the plant was designed to, and they couldn't ramp up to nominal capacity. And then they just kept losing money, and then they went out of business. Unfortunately, this is not very good. But so you need to work on logistics, and especially if you're working on the sustainable feedstock, that is byproducts and wastes and other resources than timber, because timber is not good for biofuel production. It has other places, and the price is very high. So we need to solve the logistics of the other type of feedstock. And also we have been doing studies on the role of biofuels in the transport sector when the transport sector is electrifying rapidly. So here on the two graphs on the top, you can see the volume of the transport, which is going up a little bit. This is because of the increased good transport we are expecting. But the energy need is going down. This is because of electrification. The electric engine is much more efficient. And then in the figures below, you can see that the role of biofuels in this system. And here you can see that the mitigation effect is highest in 2030 at road transport. But it's still contributing to a lot. And the highest effect in biofuels you will have in the heavy duty, because the light duty will be electrified, and in trucks, buses, and vans, of which trucks and vans are the most important. So you need to have integrated strategies. So I have you an example of technical research, what we do there. We are researching a technology. It's one of the technologies we are doing research on, which is called hydrothermal liquefaction. This is a technology that mimics how oil and gas was produced many, many years ago. So we're using high temperature, high pressure, but we don't have the millions of years of obvious reasons. So we need to understand what are the price we are paying for not waiting for a million years. And this is the quality. So the feedstock will appear in your product in some way. So we need to understand what kind of feedstock you can do, what kind of feedstock you can still produce a good product of. And because this is not a very good quality to put right into a tank, you need to upgrade that. And we need to understand the upgrading as well. We need to understand how the catalyst works, what are the requirements, how is the lifetime, how is the price. And then, of course, you can decide to upgrade it to a higher quality or a lower quality, because marine engines can take very low quality fuels. But we need to understand what are we emitting then. So we need to see whether it is a good idea or not. Another example is, for example, biorefinery. Here we have been looking into a whole different type of technology, and we modeled the techno-economics that, and put up the mass and energy balances, and then you can see the operating cost and the investment cost. And here we can see that the raw material costs are very high. This is because this is what we have business on. We are having a very high raw material cost, even if we are using residues and wastes. And I need to mention that all the biofuel production technologies need hydrogen. So where the hydrogen is coming from is important. For example, if you're using gray hydrogen, it's we don't get very much CO2 reduction, but we still need the hydrogen. The blue is better and the green is the best, but it has a very high price. So with the current regulations and the current prices, the green hydrogen doesn't make sense in the production. And this is what I had. Thank you very much.
Thank you very much, Judit. Are there any questions from the audience on the topic of biofuels, biofuel production?
So, Fiona Iversen, Norse and High Value. Thank you, very interesting presentation. A question on the feedstock. So you said you don't use wood, but could you say something more about the different types? And you mentioned quality. Would you be able to elaborate?
Yes, there is types and there is quality. What is the highest potential in Norway is the forestry residues that are currently not taken out of the forests. And it is a question, how much does it rain, how much you leave it in the forest, how do you transport, how much other things, stones and other things are you're putting into. So it has a different quality from batch to batch. That is one option. The other option is from the wood processing industry, for example, Moelven. They are exporting their byproduct to Sweden. So this is something that we could utilize in Norway. It's a lot of wood processing industry in Norway. We have good forests, and they're being used for other products and energy. And if they want to ramp up their production, they will need to do something with their byproducts, which is of value. And of course, we have the municipal solid waste and other type of residues as well.
Understand, thanks.
Thank you. Any further questions? Guy? Wait for that. Just come with the microphone.
It's Geir Brekke from Statkraft. You mentioned that green hydrogen would not be chosen. If you choose something, it should be blue. But what kind of price difference is it between blue and green? To my knowledge, there is no blue hydrogen available, and that, what is the price differences in your models?
That's a good question. I can look it up for you. I don't have it with me, but it's expected that the blue hydrogen can be produced much more at scale. The green hydrogen is the price of the green hydrogen is high because of the electrolyzers, and I don't know what kind of price they take in the model, but I can check it up for you.
Yes, I forgot to tell you, don't challenge Guy on the difference between blue and green. That can be a long debate. Thank you very much. Thank you very much, Judith. One more round of applause for Judith. And then we go over to the third and last speaker. Most of you probably know him. It's Øystein Ulleberg from the Institute for Energy Technology. Øystein is an IFE veteran, also some 30 years of experience, chief scientist at IFE, and he's the director of MoZEES. Please.
Thanks, Ingo. Wow, it's bright. So I will focus this time slot to try to answer a question on zero emission mobility towards heavy duty transport. And in this session here, we'll focus on the land-based transport. And I'll try to see if we can answer the question together, not just now, but also in the panel discussion afterwards. Is that possible to solve with battery and hydrogen technology? And so we are very introvert in MoZEES. We just look on battery and hydrogen technology, but I will show some result towards the end where we, of course, relate it, for instance, to diesel, which is the competitor, biofuels. I have a couple of slides just about the center. So MoZEES was established like the other technology centers 7 years ago. So in our last year, we have about 250 million Norwegian krones that we are spending on mainly research. 25 PhDs, postdocs, a lot of active researchers. I think we're about 200 people in the center, about 100 active on a good day, 37 partners. I won't show you the whole list of partners today, but there are 22 industry partners in the center. When it comes to the scope of work, we try to have a quite narrow scope of work, focusing on battery electric with lithium-ion batteries, and on the fuel cells, mainly on the proton external membrane fuel cells, and also on water electrolysis system, so that we have two value chains to produce the electrons for the transport applications. And then we are focused on heavy duty, land-based, rail, and also maritime. We did, in the early days of the center, do some quite thorough studies on use of hydrogen into the maritime sector on some niche markets like the high-speed passenger ferries, hence the photo there. And that is an activity that continues, and then of course the activity on hydrogen for the use in maritime continues also in FME hydrogeny. Rail has come towards the end now, so there is a large EU project ongoing on electrification on the non-electrified lines in Europe. There's also been a debate on some of the lines in Norway, so we're doing a final case study there. But today, like I said, I'll focus on this heavy-duty transport for road. These are just then the research area, the work streams in MoZEES, where two of them, research area 1 and 2, focus on the key technology developments on battery and hydrogen technology. And then in research area 3, it's more applied-oriented, and in research area 4, which I think most of the results today will be from, is more on where we combine our technology knowledge with economic calculations. So just a backdrop. We have seen that from we started the center where everyone was talking about light-duty transport with the passenger vehicles and electrification of those with battery electric. There were some efforts, of course, and there's still efforts around the world on using hydrogen fuel cells for the light-duty vehicles. But it's, at least in Norway, the focus has now gone more towards using hydrogen for the heavy-duty applications. I think MoZEES may have been part of this. Now, when you look at the fleet in the world, this is from maybe a little bit outdated, but it won't have changed that much. World Economic Forum, they reported that about 1% of the total fleet of vehicles in the world is heavy-duty vehicles, but they stand for 25% of the emissions. So it's actually a good area to start, to build up new ecosystems with the whole value chain of battery electric and hydrogen electric, etc., possibly biofuels, because the impact is large. Again, it's a little bit of a slower, old, outdated slide. I'll give you one that's a little bit more outdated in a second, but In Norway, 60,000 trucks, and at that time in 2021, just less than 1% was battery electric vehicles. ASKO is a front runner, that's why we've invited them to come here and speak afterwards with Jørn. Just some updated figures from Statens vegvesen and the Statistical Bureau of Norway. So, how are we doing towards this goal? We want to go to 50% of all new trucks to be zero emission in 2030. It's we have known about this goal all along in MoZEES. So how are we doing? Here you see we've been able to sort of stabilize the emissions from the sector, from vans and the truck sector. You see it's flattening out there in emissions. So we are not at least surpassing 4.5 million tons of CO2 equivalents. And then the new truck registrations, these are new trucks only, are increasing. So we're not at that 1% anymore, it's more like 10%. So but of course, it's just a few more years until 2030, so we need to speed up, as was mentioned in the introduction in the plenary today. So the rest of the talk, I'll focus a little bit on some of the things that we do in MoZEES, some just a brief technology perspective, and then looking at how can we look holistically at this, looking at the infrastructure challenges and, of course, the cost, the whole picture. One of our PhD students, Jonas Martin, he just completed his PhD, looked into not just hydrogen, but other fuels, comparing hydrogen to ammonia, all the e-fuels, battery electric, and this is one of his slides. And when it comes to like a 40-ton truck, long-haul truck, you can see that from a technology perspective, you're going to put in some kind of energy storage, and you have an energy conversion device on board. And this needs to fit. And you also have a load, so the main purpose of a truck is to carry a load. So you need to make sure that you don't only carry your energy system on board. So the comparison is with diesel, 1% of the total mass is it's just 1%. With carrying your diesel, and 1%, 2% on volume basis. And when you look into the battery, then it's maybe a little bit of a challenge in some cases, at least for the very, very heavy duty. The lithium-ion batteries then will weigh up to 20% of your total weight available. Now they're increasing this, relaxing this limit a little bit so that you can have a little bit increased weight, and there's been some studies at Transport Economic Institute to see what is the effect of increasing the total weight of the vehicle, because there are some impacts. And volume-wise, 8%. And for hydrogen, you can see for yourself, we focused on compressed hydrogen in MoZEES, not on liquid. I know there are developments, for instance, in Germany with Daimler, looking into liquid. Cryo-compressed can also be an option. But it's somewhat lower, but it's fairly comparable on a volume basis to batteries. But the weight is a little bit lower on the hydrogen electric. Then, once the vehicle comes in, it needs to be charged, and charged with electrons or charged with molecules. We have the hydrogen case here. One thing is to do it with a small vehicle, maybe taking 3-4 kilos of hydrogen, and off you go, and you can go for 500-600 kilometers. Another thing is to do it with a large truck, because the energy transfer is quite large. You know, if you fill a car, you're basically doing 2 megawatts if you do a fueling. And for a truck, it's even more. So here you can see some figures from some colleagues in Statkraft, presented a year or so ago, just looking into this, what's required in terms of energy per minute. So 240 kilowatt hours of energy can be transferred then with hydrogen for a truck. That's if you have a truck that has a pressurized storage tank of 350 bar. Now the next comparison is then with the battery electric. And there you can see some figures and I think this is the essence of the whole debate we should have in the panel discussion once we come to this point of discussion is where's the limit here? Because there are some limits in the capacity locally, in the grid possibly. So this has to be dealt with, although there are coming gigawatt not gigawatt, megawatt chargers. This is happening. We know this, and it's coming, but it will have a consequence on the system. And here you can see some of these consequences, you know. And it fits very well with the similar calculations we did for maritime. It's an order of a factor 1 to 7, approximately, when you look at how much energy you can transfer, batteries versus hydrogen. So we have, over the last few years, bits and pieces of research, and now we're finally collecting this in a larger study. It's a 2-year study. We call it's the Zero Emission Truck Case Study in MoZEES. And it's headed by Transport Economic Institute. It's a pretty busy slide, but I'll take you through it. I think it's important because for you to understand all the elements. You know, because next thing I'll show you are some results. And if you don't sort of understand all the elements in a model like this, it will be hard to also argue, and then we'll just pick one of the elements and argue that case. So there's truck data, there's charging station data, hydrogen refueling data, energy cost data, and we also have some data available for life cycle analysis. Those are the inputs on the top there. So we have an inventory built up over the years in MoZEES, both in battery electric and hydrogen electric. Then there's a truck cost estimator that includes the total charging or refueling costs, and out comes then we can do business cost calculations or societal cost calculations. So you see that in the bottom. And also we can complement this with life cycle analysis. And of course we'd have to do some scenarios, there are some different user profiles, and there are some policies. So it's a pretty big, mixed bag. It's hard to give an answer with 2 lines under and say, okay, this is the option. So then in this case study, we compared to diesel, also to biofuels, but for the sake of it now, diesel with some auto diesel then, with some blend with biofuel. And you can see for yourself the capacity is there. That's the base, because that's the base for the LCA analysis, and the techno-economic analysis follows. So the propulsion system then, well, the power is about 350 kilowatts in all the cases. And it can be sold with battery, electric motor, or with a fuel cell and electric motor. And this has a life for LCA analysis. That's important. You have to define the life, the operational profile, so you can do a proper end-of-life calculation. So here you see some results that show the greenhouse gas emissions per ton kilometers, cradle to grave. And I won't take you through all the details here, but EOL, end of life, you have maintenance, tank to well, well to tank, and the production, the manufacturing of the components. And you can see, for instance, the manufacturing of hydrogen fuel cells is it's lower than the battery, so it's less intensive from an environmental point of view, but the sum is more favorable for battery electric. And then, of course, we can do sensitivity analysis. And one of the issues that's been discussed is, of course, how long can the truck operate before the wear and tear on the batteries or on the fuel cells. So when do you do your stack replacements? How much do you have left in your battery after end of life? And so there's been done some sensitivity analysis on that, and you can see for yourself. Also, the grid mix in the EU will matter. So obviously, there's a very strong reason why battery electric is maybe not the option. The best option today with the existing grid mix in Europe, but it's maybe a better option for Norway. So you have to bear this in mind, because the technology is being developed not just for Norway, it's being developed for the whole Europe and the world. Final slide, maybe a controversial one. These are results that we will be discussing internally in MoZEES, so these are preliminary results. I don't think the final results will be so far away from these results. What we've done, we've taken everything in. The model we've been run, we looked at total cost of ownership here per kilometer, with taxes, without taxes. So that's the two to the left, and then one to the left with taxes, and the one in the middle without taxes, and then the societal cost. And then we have learning curves, and Kari mentioned this in her introduction. Learning curves are important, and here we can probably argue until we're green and blue what are the learning curves. But there are some basic assumptions on the operations, assumptions on the infrastructure costs. All these things are taken into account, and we're trying to project in the future. And you can just see for yourself, batteries come out a little bit better than hydrogen in most of the cases, or in all of the cases. And then we can discuss how big is this gap. As a director for MoZEES, I think we always had a policy of not ordering a study. So we try to be agnostic. So we try to be very open-minded with respect to in our analysis. So the idea is that we want to come with a solution that is zero emission, and we're agnostic to how that's done, batteries or hydrogen. And I think these trends show, and these are averages, by the way, so there will be local variations, regional variations. I think the results show that there is a little bit that we need both options, even though it might look like a big difference. I think, from my point of view, and we will discuss and we will look into regional and local markets where both options can be favored. This will be a nice, I think, starting point for the discussion afterwards. Just to summarize, when you deal with these type of studies, if it's maritime, rail, or heavy-duty transport for road, or any kind of analysis, it's important to include the full perspective, both the business perspective, the societal costs, the life cycle analysis. I could have a whole lecture on the LCA analysis done on the Chilean case where you produce the lithium for the lithium-ion batteries. It depends where you draw system boundaries. And the same thing goes for these analyses. It depends, maybe we're giving maybe this grid issue is bigger than we think. Maybe we haven't calculated in these externalities. It's very important that we are clear. So we have a system boundary in MoZEES that we have to look into. And we've tried to extend that by doing LCA analysis to sort of not just look blindfolded on business cases or societal costs, but also include, because LCA includes a little bit wider perspective. So, what's your answer? Is it possible? I think the answer is yes. We could speak about the technology. We work with the technology on a daily basis. We see it, we touch it, we feel it, it's there. But also there's an embedded infrastructure. We're competing against fossil fuels, and it will take time. And in the transition period, we'll build parallel infrastructures. We'll have some competitive infrastructures, battery and hydrogen and biofuels, but it probably all needs to be done. And it will take out time to build the infrastructure, take time to utilize the infrastructure, and it will take time to build up a fleet that's cost efficient. But we have to go towards these more economic, environmental friendly systems. So it's more now about building up the momentum in terms of production capabilities on both battery electric and hydroelectric. I think I'll leave it at that. Thank you.
Thank you very much, Øystein. Are there any direct questions to Øystein to the presentation? Needs?
So, Niels Røkke from SINTEF and Hydrogenia, as you mentioned. So, Øystein, I just wondered, you said you need to think about the electricity mix in terms of using battery electric vehicles and heavy duty because of the emission intensity of the average grid. But do you then compare the same for the hydrogen production, or are you using that as a reference for just the production or the charging of batteries, and then you look at dedicated renewable for the hydrogen production?
I think my comment was that this was a Norwegian case, right? And then we did the comparison with the EU mix, right? So we have to have, so what I want with my comment, what I meant was that for Norway, with our mix, it favors battery electric right now, but maybe not for the European grid mix if we measure on, the way we set up the LCA analysis.
I'm not quite sure if I agree on that, because I mean you can also have dedicated wind, for instance, for battery parks, which then can charge cars, and you would have the same kind of logistics and thinking as you do for hydrogen production.
Yeah, I think if you're going to, one thing is to conclude on as a whole, another thing is to conclude on a case. Of course, we can build fully renewable, both hydrogen electric and battery electric systems also in Europe. So those are case by cases, but as a whole now, we're talking 200 million light-duty vehicles in Europe. So the Europeans are very skeptical to having all that converted to electricity for battery electric vehicles, because that will be a huge demand.
Thank you.
Yeah.
Thank you. I realize we're already a little bit into the panel debate.
I'll leave it up to you.
So I think, if I may ask, I mean, we do a little we just have one more table and we just, great. So maybe we can get back up on the stage, Kari from IFA and NTRANS, and then Judit from SINTEF and biofuels. And we cut Øystein a break, and instead of Øystein from MoZEES, we take my colleague Geir Magnar Brekke from Statkraft. And then we have Arvid Løken from Avinor, Gisle Solbø, hvor er du der, fra NTNU, og hvem mangler vi? Jørn, hvor har vi deg? Jørn from Asko. Okay, you've got a mic? All right. So, just come up and... So Judit and Kari, you've already met. I start from the left here, Jørn Arvid Andersen. He is director in ASKO Midt-Norge. Do you want to introduce yourself, Jørn?
Yes, we are in this technology mecca, but in our daily work, we are working with food. We're working with transport out to our groceries and to retailers. And but we in 2018 we started to produce hydrogen on our site in Trondheim, and we are now having internal trucks. We are having 4 heavy-duty vehicles. And we also sell hydrogen to the industry.
Right. Good. The next person that you haven't met is Geir Magnar Brekke, my colleague from Statkraft and the hydrogen department. Guy is the person with the longest seniority in hydrogen and batteries. In Statkraft, do you want to say a few words?
My name is Geir Brekke. I've in Statkraft, I've worked with both batteries and hydrogen. I've been promoting Norway as a battery production location very heavily, at least 4 or 5 years ago. But the next, and that has come. And now I focus mostly on hydrogen, and I see a little bit different picture than what we saw Øystein told here, and that is more related to the energy system. And earlier today, you learned quite a lot of the investments in the grid. The grid costs will be much larger part of the energy cost in the future. I come back to that.
We come back to that, yeah, thank you. And then Gisle Solbø, NTNU Interdisciplinary Studies and Culture. Do you want to say a few words?
Yeah. Hi, everyone. I'm a social scientist, and I'm leading the research area on deep decarbonization and societal changes in NTRANS. So there, we're trying to kind of follow up the things that Kari has also presented, and how can we think about these more radical changes and the underlying practices that the transport system is built on, and it's producing a lot of the transportation demand. Yeah.
Thank you, Gisle. And then we have Arvid Løken from Avinor, representing the Holy Grail, as we used to call it in biofuels, the sustainable aviation fuel.
Sure. Yes, I'm working with in the sustainability department in Avinor, and we work hard to reduce our own emissions from airport operations, snow removal, terminal heating, but we also engage in the green transition of the aviation industry. I mean, that's where the big emissions are. So it's the topic that I'm dealing with, the sustainable aviation fuel, which is both biofuel and fuel from other resources like electrofuels.
Yes, thank you. I think I want to start off with something that we looked at in Silver Green Fuel some 10 years ago, basically the distribution of fuels used in the different sectors, published by Statistics Norway every year. The 2023 figures will be published in 2 or 3 weeks from now. In 2014, I remember it was some 9 billion liters of petroleum products being used, half of that about roughly going into transport. At the time, there wasn't a lot of blending. I would expect that the fuel consumption is going down slightly, but it's not even near to where you think it would be or should be. So maybe starting with NTRANS, because you're looking at the whole energy system, it's only a few years until 2030. There's a big chunk of fossil energy still in the transport system. In short term, what should we do to work our way out of the fossil fuels? Recommendations.
Well, there are sort of two quick options, or there is still to go for electrification as much as we can. And as Judith has already presented, we can use a lot of biofuels. Sort of that's very easy, but that doesn't take us the whole way. But until 2030, we need to use as much as sort of battery electric as possible. But we also need to think perhaps differently on the way we use transport, so that we can travel less, use more public transport, and perhaps I can then give the word to Gisle, also representing NTRANS.
This sounds like you, because you presented some of these radical scenarios, where you get a major technology change and a societal change. Is there something that is a low-hanging fruit at all, or does it always generate a lot of stir when you try to go into that direction?
No, I think there's an untapped potential there on the more radical types of transformations that is perhaps not explored well enough within current policy, at least, that tend to build a lot on existing kind of ideas and how we will grow in the consumptions, where we're not putting enough effort into exploring also perhaps the more avoid and shift strategies within the transport sector. I think the recent report, for instance, by the Climate Commission has done a good job in kind of fronting these alternative strategies as well. So I think there is a willingness there among the public, and also seeing their travel behavior, and also more and more kind of wholly on how they purchase goods, and all of this in a more kind of a climate context that can also be part of creating some good changes.
Guy, you were mentioning this, the electricity demand and the use of energy in the transport sector in general. So if we electrify, where do we see the challenges?
It has been mentioned, but earlier today you heard it was talked about energy and power. So the energy, the kilowatt hours, and the power, it's the capacity of transport, getting the energy to the final destination. So that is the grid. So in the short term, the biggest bottleneck is the energy transport. It's the grid, and you will see the grid cost increase more and more and more. But you will also see the kilowatt hours, the price will go down if you look at in a 10 years perspective. So the challenge is to utilize the power or the grid best possible. And how to do that, that is the question.
Yeah, so hydrogen, obviously, also as introduced by Øystein, that is obviously one of the solutions. Talking about societal change or, let's say, customer acceptance, Jørn, you represent a company who is really a first mover in the adoption of hydrogen fuel cell electric vehicles. You've been doing that for a couple of years. As part of your ongoing business, so it actually has to deliver. Can you share some experiences from that period, now that you have been more or less the test bed for hydrogen fuel cell electric vehicles?
But first of all, I would like to complement the question you had earlier. ASKO is aiming to use battery electric vehicles as much as we can, as Kari said. That we see that in this geography and topography in Norway, this could be sold by 80% of battery electric vehicles. The rest is based on hydrogen, and we also have some biogas. Some experience with our test of hydrogen vehicles. We have owners that are willing to pay extra to start up with new technology. So when we choose hydrogen to start for our 4 vehicles, was based on that we bought a concept vehicle that was not fully tested out. It was a risky business, and the result was that we had major problems. When the vehicle was running, it was quite nice, but we had some problems with cooling and also with the stacks. But the company we did buy the fuel cells from, they was the Cummins come on the base and buy this company. Now this have changed a lot. They are now focusing a lot of this new technology, and we have 5 fuel cells. We have 4 cars and 5 fuel cells. That one of this in spare. They have now said that they will change all those fuel cells to the newest technology. These fuel cells have been running in a minor place with heavyweight and 1 million kilometers. So we are very sure that this will be good choice for us. Also, we have made an order to Scania with the 2 new fuel cells. They are now building with this same fuel cells from Cummins. So to produce hydrogen is okay. That was a risky business also because of this accident in Kjørbo. But now it's been running in 5 years, so that's okay.
Right. So you say 80% battery electric, 20% hydrogen, but you're also operating a fleet of internal combustion engine-based vehicles. And those are using biofuels one way or another through the blended mandate. So this is where the third option, I would call it, comes in, biofuels. Judit, do you see, I mean, we're talking a lot about hydrogen here, we're talking a lot about battery electric, but we still have most of the transport running on diesel with biofuel. What are the synergies here? I mean, where is this going? I mean, you showed some on some of your slides, but can we exploit a little more out of this in the future?
Yes, we need to, for the first, we need to find the synergies, because the green transition will be very, very costly, and we need to reduce the cost, and then that's why. So one synergy is that the hydrogen is needed in biofuel production as well. So for example, we could explore if we could utilize some of the hydrogen, maybe from excess or maybe planned in a way. The hydrogen, what does the hydrogen in biofuel processes? They increase the efficiency. So half of our carbon from the very limited resource, biomass, is going out as CO2 if we don't use hydrogen. And if we use hydrogen, we can put it into the fuel and then put it into the... On the other hand, of course, the internal combustion engine has its problems. It's also the efficiency. So where we can, we should do something with that. But there are some places where we cannot really do any other option. I mean, it's very good that you had a very nice experience with the hydrogen. This is promising. But I'm sure Arvid doesn't have the same experience.
Yeah, because you're mentioning hydrogen in the use of biofuels. And then when we talk about aviation fuels, we are really starting to put in some hydrogen when we use when we produce biofuels. So Avinor has been blending in sustainable aviation fuel at Gardermoen for, was it up to 10 years, or quite a number of years. Is still doing that, and I guess it is increasing. How does it look like on the sourcing side? I mean, you will probably you have to import all of this. How does that situation look like?
Yeah, sure. I'll just briefly on the Norwegian story of introduction. I mean, we had the first flights with Biojet in 2014, and Oslo Airport was the first hub in the world to blend Biojet into the kind of fossil fuel system in 2016, and then there was voluntary kind of phasing in, but from 2020, Norwegian government was the first in the world to kind of come up with a SAF mandate, with a Biojet mandate, still at 0.5%. But it is all imported, as you mentioned, mostly coming from Neste, produced in Finland in their refinery. And Neste is also building up refineries elsewhere, Rotterdam, Singapore, increasing capacity a lot. And they say that they, as a company, will be able to supply the European kind of need until 2029. But others are also building kind of HEFA, HVO factories based on used cooking oil and animal fats. But the problem is that we will run into feedstock constraints when it comes to used cooking oil and animal fats. So right after 2030 is the estimate. We will need to bring in other feedstocks, inputs into producing sustainable fuels. And then we'll need electrofuels, we'll need fuel produced from municipal solid waste, for example, not recyclable plastic. So we're looking into all those options, but the current production method will be fairly limited in the long term.
When you're saying which is now called RFNBOs, renewable fuels of non-biological origin, that are the electrofuels and such, we're looking at significantly higher production cost, obviously compared to fossil, but also to the existing HVO type fuels. So, I mean, referring to you, Gisela, I mean, Arvid says they're blending in 1% right now. So if you blend in 1%, half a percent. If you're at 0.5%, it has a small effect maybe on the total sales price to the airline. But by the time you go to a percentage or 1.5%, it makes a difference, starts making a difference. And then we're going quickly into that willingness to pay, because for the airlines, fuel, that is basically, it's all the fuel game. It's their OPEX costs, so they go up. And then the consumer has to pay for the higher tickets. Do you think that we will do that? Well, or what's going to happen?
I think, well, the main problem here for me is not the high price and the willingness to pay, but some people will be willing to pay, and you will kind of end up with a kind of economic divide in who is flying and who is not flying. So on a general level, of course, we want to decrease the level of flying totally in the world. We don't want to end up in a situation where price is kind of the only kind of ticket into flying, and some proportions of the populations are kind of highly mobile and can harvest the benefit from that type of living, and then we have people within the lower income segments that cannot access this type of transport. So I think that's also, if we're only thinking about price, we also need to think about kind of the distributional effects of this type of kind of price incentives.
Yeah. Okay.
Yes, I'm always curious when we talk about this extra cost that the renewables will cost. It's more costly just because we still subsidize the fossil fuels. So it's actually, the transition can go much faster as long as we stop subsidizing the fossil. So it's more, we should get higher price for the fossil, because that is what we actually do this for. It's the energy crisis. It's because we have too much emissions of CO2 and other things from the fossil industry. So we should rather start talking about stop subsidizing the fossil fuels.
Yeah, so Kari, if you take a guy's suggestion now, so you go to just literally any Norwegian street, say, hey, use at Avinor's airports, if you buy that ticket from SAS, you're subsidizing, and now you have to pay more. How do you do that communication exercise? I mean, in view of that, have you had any, I mean, as part of that societal change debate?
I couldn't very easily answer that, but I can say something about the cost of CO2, because if we increase the cost of emitting CO2, then it will be much easier to have the implementation and I think there is actually a willingness to pay if all contributes and that the emitters actually have to pay. And then also the low-income groups often have less sort of emissions, so they pay less. So then the transition will also be more just and yeah.
So now more an overall question to all of you. So you have been presenting that, actually some of you have been presenting that. So you started these FMEs some 7 years ago, in 2017, and you've all seen that things change on the way. I mean, the landscape is changing as we go along, and we're trying to do major changes here. Some of them are economical, so no problem. Some of them will need subsidies, or they will need some sort of policies in place. Is there any, I mean, what is the role of the FME here? I mean, we need to bring forward some ideas, or we need to at least suggest something for the policymakers to help us lift this transition, and something that can be stable also in a predictable future. So as we're developing assets, production assets for biofuels or for hydrogen or for battery production for that matter. Do you have any views?
Yeah.
Start with whoever. You did?
Yeah, there's several roles of the FMEs. One is to support Norwegian industry. The other is to contribute to science-based debate. It's a lot of decision-making based on dreams or views or lobbying. And we need to contribute to putting the science on the table. And also we can do cooperation to find new ideas, maybe together with the FMEs. It's a very good arrangement here that we do so.
Yeah. Can I add?
Yeah, yes, Arvid was first. So.
Okay. Now, looking at liquid fuels, and it's currently imported, but many point to Norway as a good location for those kinds of productions. I mean, electrofuels, we have a high renewable share, better positioned for that kind of production than in most other European countries. And also for biofuels, we have the large Silva Greenfield demo plant, for example. So we're kind of fairly well positioned, but development activities are needed, kind of lifting the TRL, coming up with new solutions, actually getting this realized in Norway from different feedstocks. So I see a role for the FMEs there.
So, are there questions in the audience now that you have the opportunity to fire off your questions directly to the panel participants? Do we still have a mic somewhere? There's over here.
Can you hear me? Yeah. I have a question about the fuel for planes. What exactly, you said 0.5%, so that's very minimal. What's the effect on the efficiency? Does it have an effect?
I mean, for the propulsion?
Yeah.
No, it's the energy content is at least the same as a fossil fuel.
It's meant to be matching the energy content of the fuel? It's meant to be matching the energy content.
It is matching.
It is meant for that, yeah.
I mean, there is a thorough process in assuring that the technical requirements are met, and it is met.
Is that something that is easy when you were mentioning that you could use the trees or material? Is that something that is easy to match? Because it seemed to me like the fuel for engine is actually very efficient. That's the purpose of using this particular kind of fuel, because it's got a very high energy per mass. So I'm just wondering how easy is it to match with the biofuel?
Yeah, it's both energy content, it's freezing point, ignition point. I mean, lots of technical requirements, and they all have to be met. I mean, no kind of compromises on that. And if there is a difference today, actually biofuels has a slightly higher, I've heard, energy content than fossil fuels, but almost the same.
Okay. Yeah. Now, I was wondering about this because of comparison to what happens in the car, where originally when you were adding ethanol in the car, you would have less power and less properties. So in the case of the plane, there was an ask for you guys to have the same properties in the end.
Yeah.
They've used it for fighter jets also. Yeah.
Judith?
Yeah. Actually, it's more or less the same fuel. It needs to be certified, so it's ASTM that certifies. So chemically, is very much similar fuel. It's not the same, but it's similar. But when you mention ethanol in cars, that's chemically totally different fuel. It can be used because it can be burned, and it can be, but you cannot use 100% unless the engine is designed for that. But for aviation, the fuels are certified between 10 and 15%, depending on the production. So they need to make sure that you can park a plane if the engine is crashing. So you need to be safe. So it's a very thorough process.
Thank you.
Is there another question? Oh, Øystein. Sorry, I don't see you.
Are you scared? I have 20 questions for you. You saw them last night. I'll pick one, and you are prepared for this one, because I showed everyone the case study we did. And my question then, with those results, I showed hydrogen and batteries against each other. So the question is, should we pick an option, or should we go for both? Should it be weighted? Can you just comment on your thoughts on this? Large and high and low thoughts.
I think that's a question for Jørn, I think.
We have discussed a lot. If I could take an example, if you have time to that. Last Friday, we received our newest battery electric vehicle. It has a range of 350 kilometers, theoretically. And we drive it from Trondheim to Oppdal. We have 16 customers on in the vehicle. And it was calculated that we should have 12% energy left when we come back to Trondheim. And we said to the driver, please charge in right after Oppdal. He came to this station, and the charger was out, was error, didn't work. So it's starting a heartbreak for the driver, and he came back to Trondheim at 8%. That was lucky. So we have wondered. We are sure that there is enough power in Norway, but how can we use it efficiently? We can make an energy hub that we can charge in 4 hours of this 24 hours a day. We should have this agreement that the rest of this day or during the night we should produce hydrogen. Then we have a complete energy hub. That's also we could have a biogas station in this. So that's our idea to solve it. We see that we are transport food out in the islands out from Mo i Rana. If the ferries there should go on electricity, there is no power for us, our vehicle.
Maybe Kari, you want to follow up?
Yeah, I think I also want to comment on this because I don't think there is sort of one technology that fits all. I think we will need more than battery electric vehicles. I think we will need, and our analysis shows that we will need also hydrogen. It sort of serves different purposes. Longer range doesn't use that long time for filling, and we can also produce hydrogen when electricity is not, or the power capacity is available. So this means that we need both, and I think it is a very good idea to start now to build the infrastructure for a certain transport corridor so that we can have more experience. And I think it's time to do that now.
2 seconds left on the clock. You get to close the session.
I would like to support that, and that is also in the name of utilizing the grid best possible. Have these stations, at least for heavy transport, with a combination of the zero emission or low emission fuels. That will be the best. So for the Norwegian government, support these combi stations of at least battery, hydrogen, biogas, biofuels as fast as possible. Then you can get rid of the fossil fuels.
Thank you very much. This concludes the session. Thank you very much for attending this session, and a round of applause for the panel participants.